the math happy hour. Please, can you let me know if you can hear me? I'm so sorry.
Yes, sir. You're good to go.
Thank you so much. So, so today we're actually this is our last recording of the semester. We're gonna be covering the final exam review, and let me get started. So, we're the review covers starting from chapter 2, which is sets, and then it ends on chapter 9, 10. We don't cover all of the chapters, we did skip some of them, so let's just go ahead and review some of the exercises that we saw in the chapters that we covered. This was one of the usual questions. Use the roster method to form a roster method to represent the following sets. For example, if you want to represent the set of natural numbers less than 5, then um, the way that we would do this is to write down 1, 2, 3, 4. And actually, this is the set of natural numbers. These are all of the natural numbers. The natural numbers do not include 0 because 0 is one of those numbers that cannot be represented. So it doesn't really, usually when we represent 0, we say that it's empty, that there's nothing. So it's not included on the naturals. Observe that the final answer would be like 1, 2, 3, 4, and then included in the braces. Make sure that you use those specific type of parentheses. That usually I call it, some people call them curly brackets or braces. So this is, do not put it in parentheses. They must be exactly like that. And also make sure that each of the numbers is separated by a comma. So the idea is that if you don't put the commas, it's considered like a single number, like if it was like 1,234. Rather than when you separate with a comma, it emphasizes the different objects in the set. The next example says the set of negative integers greater than -4. So now the word integers now includes 0 and all of the negatives. And so the numbers that are greater than -4, numbers that are greater always appear to the right when you put them in order. So if you have -4, greater than -4 would be -3, -2, and actually we would stop there because they're supposed to be negative. So not only do they need to be integers, they also need to be negative. So our answer is -3, comma, -2, comma, -1. Okay, let's move on to the next one. We say that a set is well defined if it is possible to determine whether any given item or object is an element of the set. So the objects that are inside the set need to be clear. It cannot be subjective, it cannot be ambiguous. For example, A, it says, identify if the set is well defined, the set of math faculty at EPCC. Well, this is actually something that you could go and track and see which are the faculties. So there's probably a list on the website, and you'll be able to identify who is a faculty and who is not. So this is a well-defined set because if you give me a name of a teacher or of a person, you can decide if it is a faculty or not. On the contrary, on B, we have the set of great cars. Well, how do you define what a great car is? We can already see this is a bit subjective, huh? Maybe someone that is very fond of trucks would say that there's a great truck. Maybe somebody who really likes Ferraris would say that a Ferrari is a great car. So this would be an example of something that is not well defined because the word great is not specific and it's more subjective. All right. Related to sets, we use this symbol that looks like an E, and it represents that something is an element of a bigger set, that an object is an element of a set, that is a part of a set, it's a member of a set. We also have the symbol not an element, which basically kind of like the opposite. You just cross it with a diagonal. So in these examples, we have some elements and then the symbol and a set. And we want to say whether the element to the left is a set, is a member or an element of the set on the right. So we can, and this is pretty simple. This is why we like to have what we call the roster method. The roster method is when you make a list of the elements. So technically, by looking at the set, you could see what is inside, and we easily see that 5.2 is not in there. So this is a false statement because this symbol would say that 5.2 is, but it's not. It's not part of it, huh? The next one, so I think I should have that answer. So the first one is false. The next one is a little bit more tricky. Remember that the I represents the set of integer numbers. This is positive whole numbers, 0 and negative. And because 101, it's a whole number and it's negative, it is considered an integer. So this is indeed negative 101 is an element or is a number part of this set that we call the integers. And last, W represents the set of whole numbers. This is 0 plus 1, 2, plus the naturals. And again, usually the word whole means that there's no fractional parts, that there's no partial part. So a decimal number typically is not a whole number. It's like a number plus some decimal, plus some fraction that is missing the entire thing. So of course, this is actually true because the way that the statement is written, it says 2.5. It is not a whole number, and that is correct. So very important. Initially, when I started the question, it seemed like, oh, well, 2.5, it's not a whole number. And precisely the symbol indicates that. So the whole, all of this is true. We call it a statement. So this statement is actually true. Okay, let's move on to another example. So we also talk about finite sets. And to determine if a set is finite, we identify what is called the cardinality. So the cardinal number of a set is the number of elements in the set. So for example, what is the cardinal number of the set below? And if we count how many does it has inside, so it would be 1, 2, 3, 4. Then we can say that the cardinal is actually 4 because it has 4. We write it, we put n, and then we put it in parentheses, and inside we put the set. So n parentheses A means the amount of objects inside the set A, the cardinality or the cardinal of the set A. And the answer is 4 because there's 4 in there. And then here, let's find the cardinality of these sets. So J, the cardinality would be 2 because he has 2, 2 and 5. B, now B is kind of tricky. Do you guys notice that we have the dot, dot, dot? So often we don't write down the entire list of numbers. And we just put the dot, dot, meaning that it follows the same pattern. So how many numbers do you have between 3 and 31, including 3 and 31? Well, there's actually a formula where you can subtract these two and then subtract 31 minus 3, and then you add 1. Because basically when you subtract 31 minus 3, it gives you everything that is after 3. It's like you cancel the 3 itself. So you need to add an extra one. So 31 minus 3, that would be 28. And then plus 1, so that you include the 3, that would be 29. So the answer is 29. So that's an easy trick. Whenever your numbers are in increasing order, like they're consecutive, like one at a time, like 3, 4, 5, you don't skip a number, then you can just subtract the endpoints and add 1. For T is a little bit easier, huh? We can actually count them. However, with sets, sets are defined based on the elements that you have inside. So if you recall, sets do not depend on repetitions. So even though the 3 is repeated twice, it should only be counted as 1. So the cardinality here is actually 3. I have it right below. Because if you were to ask me, like, describe the numbers that are in the set T, then I would say 3, 7, and 51. So there's only 3 different ones. It doesn't matter if you repeat the 3 twice, it's the same object. So it counts as 1. So when we have sets, repetitions are usually eliminated, and you're not supposed, this would be a bad writing. You're not supposed to repeat an element. So we need to correct it and have only 3, 7, and 51 because the cardinality is 3. We say that two sets are equal only when they have exactly the same elements. For example, here, D, E, and F, this set is actually not equal because it doesn't really have the same elements. However, we're gonna say that two sets are equivalent when they have the same amount. So in the previous examples, these are not really equal because he had, well, actually, sorry. Somehow when I saw it, I thought it was A, B, and C. I changed it. So these two are equal because they have exactly the same letters, even if it's in a different order. That's another thing with sets. A set does not need to be organized in order, not in alphabetical, not in increasing. So as long as it has exactly the same letters, the same objects, it's exactly the same set. But more often, you have sets that have different objects, but they have the same amount of elements inside. So in this case, we're going to say that the sets are equivalent, and we represent it by putting this wiggle line in between. And the condition to be equivalent is that the cardinality has to be equal. For example, here we have a set which has the vowels, and then we have another set that has numbers, and you may count and realize that each one has 5. So these two are actually equivalent. They're not equal because they have, one has vowels and the other one has numbers, but because they have the same amount of objects, 5 numbers and 5 letters or vowels, they are considered equivalent. These on the right would be an example of two sets that are not equal and not equivalent, because the first one actually has only 3 objects, and it has, for example, -2. The other one has 4 objects and does not contain -2. So the fact that we found something that is in one but is not on the other already makes them not equal. And because this has 3 in total and the one on the right has 4, makes it not equivalent. Now, we also talk about complements, subsets, and Venn diagrams. So a complement of a set is the opposite. I always say the opposite. But the formal definition is that it is the set of all of the elements in the universal set U that are not in A. So if you have a set that has all of your elements, that's called the universe, and you have another set which is A, the complement is represented by an apostrophe on the top, a comma on the top, and it's going to be everything that you left behind or everything that you left outside. Let's look at an example. This makes it easier. So we have an example where the universal set has numbers 1 through 10. So now, no, we're not going to consider any other numbers for this specific example. So nothing past 10 is not considered, no decimals, no negatives. So only numbers 1 through 10. That's what we give the name of universal. The idea is that your question is going to restrict to that universe of numbers. And so we have a set called S, and it contains 2, 4, 6, and 7. And we have another set T, which is actually represented in a different way. We call this the um, oh, the name of it is escaping to me. So instead of giving you the list, we actually, I think it's called builder, um, set builder notation. So instead of giving you the list of objects, we give you a variable that represents any of the objects. Then we put a line, a vertical line, and to the right of it, we give you the description of what each X, what each object has to represent. So X has to be less than 10, and X, it's an element of the odd counting numbers. So it has to be less than 10 and it has to be an odd counting number. So find S prime, which is the complement, S apostrophe, which is the complement of S, and also find the complement of T. Well, for the complement of S, notice that if you look at 2, 4, and 6, we left behind, we didn't include all of the other numbers. So the complement would have the ones that we didn't include in S, starting with 1. So 1 would be part of the complement. 3 would be part of the complement because it's not in S. 5 would be part of the complement. 8, 9, and 10. So a simple way to kind of like check your answer would be that if you add the complement plus the original plus S, it has to give you the entire universe. In other words, if you add up all of the elements, it has to give you the total numbers of elements. That's a simple way of checking if your answer is correct. Also, on the set T, the first thing that you want to do is write down the list of numbers that is in this set. So this description should be enough for you to say which numbers are part of this. So for example, 1 would be in T because 1, and I actually have the answer here. We're not the final answer, but instead of writing it in this descriptive way, I'm actually listing the actual numbers that are in the set. For example, 1 is part of T since it is less than 10 and it's an odd counting number. 3, 5, 7, and 9. So of course, the numbers that were left that we didn't put in T, those are the ones that are in the complement, and those are the even numbers because T focuses on having odd. So the complement has 2, 4, 6, 8, and 10. That's what I like to think of the complement as the opposites because odd numbers and then the opposite would be even numbers. All right, let's move on to another example. As I mentioned, we talked about subsets. A subset is basically a portion of a larger set. And so the mathematical definition is that A is a subset, and we put that symbol of B, if and only if every element in A has to be also in B. So every object on the left has to be on the right. Because that's exactly, if it is a subset, then anything that is contained in A had to be on the larger one. That's the idea. We use the word proper subset to say or to represent that A is strictly smaller than B. So not only every element of A is in B, also they're not equal. So that if you take those two things into account, A has to be strictly smaller than B. These symbols are pretty much as less than or equal or strictly less. When you have numbers, you could say like 3 is less than 5. So this would be less than 5. And then if you allow them to be equal, then you put that, actually that line below, it stands for equal. A is equal. So in the first example or the first symbol, A could be potentially equal to B, and on this symbol, A has to be strictly smaller than B. The examples are this. Notice that 5, 10, 15, 20 is a subset of this larger one. To check, well, actually, we're supposed to determine that. To check, I said notice because it is true. every number that is on the left will have to be also on the right. And we can just look each one of them is actually there, huh? So the answer for A is actually true. Well, I'm just gonna give you the answers because the other thing has too many words. So the first one is true because each of these four numbers is also on the right. B is one of those questions where you need to remember the definitions. So W represents the whole numbers, which is 0, 1, 2, 3, all the way till infinity. And the natural numbers does not contain zeros, so it's 1, 2, 3, 4, 5, and all the way till infinity. Well, this statement is actually false because, in fact, the natural numbers is smaller than the whole numbers. How would you prove this in a simpler way? Well, if you find an object that is in W but is not in N, that automatically makes this statement false. And the example would be 0 because 0 is considered a whole number but it's not a natural number. Okay, moving on to C. Now, this is actually true, huh? We can see not only each of these numbers is in here, they're exactly the same ones. So yeah, this is a subset of this because each number is in there. In fact, they're equal, which is why it's appropriate to put the equal line below. But even if they're not equal, you could still put the line just like I did in this example. Because when you put this, when you put the equal, it's all that you check is that each of the numbers on the left is on the right. All right, if we move on to example D, this is more of a technical example. On the left, this symbol represents the empty set, which it's the equivalent of the 0. So the empty set is the set that has no elements. And by definition, this is a subset of every set. Another example, E. Oh, let me go here. E. Now, these, let's check. This is actually true as well. It's pretty much, it's exactly the same thing as A, but notice that the symbol has changed. Now, it is still true because each of these numbers, it's on the right, and also they are not equal. So when we put this symbol, basically, it's easier to remember that the set on the left is strictly smaller than the one on the right. And we can see that right away because the set on the right has more numbers that are not on the left. F, it says the whole numbers is strictly smaller than the natural numbers. This is false because to use this symbol, you need that everything on the left has to be on the right. But we already saw before that 0 is not, it's in the whole numbers, but it's not in the naturals. So this is false for the same reason that the first one, that B was false. And last, G. Now, this statement is actually false. Notice before we had it here, and before it was actually true because every number on the left is also on the right. But when you put that symbol, you want to say that the one on the left is actually strictly smaller than the one on the right. But that's not true, huh? So then G is false. Okay, so these are our Venn diagrams. We call these operations that you could do with sets. So the first one is the intersection, and this is the set that has the elements that are common to both A and B. So basically anything that is on the intersection, it has to be on both. And in a diagram, you represent, so each set is represented by a circle, and the ones that are common to both would be what we call the overlap. So it's this area that is in gray, darker blue. The union of two sets, this is equivalent to somewhat of a sum. So this is the set that contains all of the elements that belong to A or belong to B or to both. So this is how you write it. X is an element of A, or X is an element in B. So this is kind of like the formal definition, the set builder notation. But here in the diagram, basically it is the entire area that covers A plus B. Very important that when we look at this area, when you talk about area, you're not supposed to add twice. You just add each piece once. Let's look at examples. So I have a set A, which is has numbers 1, 4, 5, 7. B has numbers 2, 3, 4, 5, 6, and C 3, 6, 9. We want to find the intersection of A and B. These are the ones that are common to A and B. So notice that 4 and 5 appears on both. So the intersection of A and B is the set that contains 4 and B. The intersection of A and C, well, if you compare A and C, they don't have anything in common. So we would say there's no element, but for set, the equivalent to say that there's no elements is actually the empty set. I always ask my students, don't write it as a 0. It looks more like an O with a line cross. That way you don't confuse the empty set with like the number 0, because it's different things. Another example of the union is exactly the same sets, but now I'm going to do the unions. If you do A union B, so these are the elements that are on one or on the other or both. And it may seem surprising, but remember that when we talked about sets before, I mentioned that we don't repeat elements. So you're not meant to repeat those things. That's when you look at the diagram, the Venn diagram, let me go back. This one, I mentioned it's the total area, but without repeating the area twice. So in other words, if something is already counted, we don't need to count it again. And so notice that 1 would be part of the union, and then 2 as well. 3 because it's on the right. 4, even though it's on both, we count it once. 5 is on both, we count it once. 7 and then 6 as well, huh? So it's kind of like a sum, but we don't repeat elements. All right, moving on to the next one, A and C. So the union of these two sets, actually, this basically looks like a sum because it adds all of the elements that are on A plus all of the elements that are in C. So since we have no repeated one, the union has actually the sum, literally the sum or the union of both. Okay, moving on. So more in detail about Venn diagrams, the complement of a set. So usually the universal set is represented with this rectangle. The rectangle, we put the U. So everything that is on this question must be in this rectangle. And then each set is often represented by a circle or an oval. And remember that the complement would be everything that you left outside. So graphically, this is actually the outer area, the area that is outside of that circle. An example to identify graphically each of these each of these sets, like the union, the intersection, the complement, would be this. So we have a set, and let me explain it. A actually has only 3 objects. So it has each of these symbols, the dollar symbol, I always forgot that one. The pound symbol, I think, is called triangle. And then B has actually everything that is inside on it. So 2, 4, 6, and triangle. So one can say B has 4 elements, 4 objects, and A has 3. And notice that we put the triangle in the middle because it's on both of them. So if I ask you to find A, I just describe it. It would be those 3. And then if we do the union, A union B would be these 3 plus the extra 3 that I have it included. So B actually has 2, 4, 6 and triangle. So the union, notice that even though the triangle is on both, we don't repeat it twice. We also have the intersection, and I did mention it, the intersection, only the triangle is in both. So A intersection B would be that object. The complement of A is everything that is not in A, which is 2, 4, 6 that are part of B, and outside of B and in this whole rectangle, there's a 7. So we got to include that 7. And then the complement of B would be everything that is outside of B, which is pound symbol, dollar symbol, and 7. All right. This is another typical example. Remember, the big square, big rectangle represents the union, and the union must contain everything, all of the symbols, all of the numbers. So the union contains all of the numbers that are inside not the union, the universal set contains all of the numbers and all of the symbols that are in the whole problem, including these two, which is not in any of these circles. And then A would be the numbers that are part of A, like 1, 3, 4, 5, 6, and 8. B would be the numbers that are in B. Let me see if I can. There. So these would be 4, 5, 6, 7, 9, and 11. C, it's the numbers that are inside the circle that represent 6. So this is 6, 8, 9, and 12. The union of A union B would be the numbers that are in the union or in the sum of both areas. So you could see basically everything that was in A and adding 7, 11, and 9. And the intersection of A and B, wow, I don't know. I apologize about that. The intersection is actually the ones that are here, 4, 5, and 6. The intersection of A and B. Remember, the intersection basically is the ones that are in both, the common elements. So this is 4, 5, and 6. I believe it's like a continuation of the previous one. So if you do A union C, that would be the sum of the elements that are in A plus those ones that are in C. Notice that I did not highlight a 9, but 9 is also part of the answer. B intersection C, these are the ones that are common to B and C, which we can see is the overlap of the circles for B and C that has numbers 6 and 9. Now, just like how you add numbers, you can also have the union of multiple sets. So this is A union B union C. A simpler way to describe it would be to say, add all of the elements that are in A, B, and C. And so almost everything is highlighted. It's part of the answer, except 2, the number 2, because it's not a number that is in any of those circles. And the intersection of all 3 would be the one number that is in all 3 circles, and that is only the number 6. We also have special formulas. Let me increase this a little bit. These are called the Morgan's formulas. And there are special formulas that tells you that if you have the complement of a union, this is equal to the intersection of the complements. So it gives you a way to find a set in different ways. You can first do the union and then the complement, or you can do the complements and apply the intersection. And simple way of proving this would be by looking at the Venn diagrams, or to convince ourselves that this is an actual equality. You could do the intersection of these two, the union, which is the whole sum, and then the complement would be the whole area in blue. So this represents the set on the left. And the set on the right is actually, let me see if I'm still, the set on the right, um, you start with the complement of A, and then you do the complement of B, which I have now in yellow, in green. And the intersection of those two would be the combination of colors, green and purple, which actually I'm putting in brown. So notice how the brown area is exactly the same as the blue area. So because in the diagrams, it represents, it gives you exactly the same area. This is how you would show that these two are equal. This is actually the same one, but now instead of using Venn diagrams, we're gonna use numbers. So the universal set has numbers 1, 2, 4, 1, 2, 3, and 4. A has 1 and 2, B has 2 and 3. And we could see that 2 in the middle, 2 is in the overlap, and 4 is outside. Well, when you do the union of A and B, you're putting together 1, 2, union 2 and 3, and then the complement. And so the union of 1, 2, 2, and 3 would be simply 1, 2, and 3. We don't repeat. And if you do the complement of that, that would be whatever you left out, which is just 4. Well, on the other side, if you do the complement of A, this is everything that is outside of A. A contains 1 and 2, so you left outside 3 and 4. And similarly for B, B has 2 and 3, you left outside 1 and 4. And when you do the intersection of those complements, the one that is in common is 4. And since we got 4 on the left and 4 on the right, then this would show that these two are equal using these numbers. Okay, so as I mentioned, we call these the Morgan's laws, and they're very useful to find different sets. Now, I overdid it with the Morgan's laws. Let me just skip till the next chapter. Or this is actually a great example. I actually don't want to skip it. One of the typical, because this might be a final question. It says an application. How do we use these Venn diagrams? If you just look at the diagrams, it looks very abstract. Like there's no way I can use these diagrams to solve a practical question. Well, this is a question that we can solve using these diagrams. It says a music teacher has surveyed 495 students. The results of the survey are listed below. 320 students like rap music, 395 students like rock music, 395 likes heavy metal music, 280 like both rap and rock, 190 rap and heavy metal, 245 both rock and heavy metal, and 160 like all three. So you basically have the numbers of individual likings. Everybody that likes rap, everybody like, and then also you have the numbers that like two of them, both rap and rock, both rap and heavy metal, and both rock and heavy metal. And you have the number that likes all three. And the question is, how many students like exactly two of the three types of music? Like only rock music and like only one of the three types of music. The problem that the reason why the answer is not obvious based on the previous numbers is because maybe when I tell you how many like, let's say, rap, some of these people that like rap also likes rock and also heavy metal. So these numbers do not tell you the answers to exactly these questions. So I would like to know the ones that like exactly two, but not three. So what is the number of people who likes only two different types of music without not liking the third one? And to solve this question, we create our Venn diagram. Each circle is gonna have one of those type of musics: rap, rock, and heavy metal. You start on the bottom. How many like all three, which is 160? That's how many people you have in this overlap. And then the next would be how many like both rap and rock. Well, 280 like rap and rock, but I already count 160 out of those 280, because the people that likes rap and rock, some of them also like heavy metal. So to find those ones that do not like heavy metal, I would need to subtract 280 minus 160. That gives you 120. And that's the number that goes in between rap and rock in this area without including all three. And you go on like that for each type, huh? So out of the 190, subtract the 160, and that tells you how many only like rap and heavy metal. And similarly, out of the 245 that like rock and heavy metal, subtract the 160, and that will help you find how many like only rock and metal. And let me check this math. It should be 85. So the answer on the picture here is right. Over here, it looks like a 75, but it's 85. So, but just by looking at the picture, you can tell that the ones that like exactly two, but not the third one, is the areas that has the 120 in blue. Those are the ones that like rap and rock, but not heavy metal. The one in green, these are exactly the ones that like rap and metal, heavy metal, but not rock. So these areas, these numbers are actually, if we add them, this is the people that likes two types, exactly two types, and no more than two. So that's actually my answer for the first question. Now, I can now use the total numbers to identify those ones that like only one type. For example, if I start with the 320, this is the people that likes rap music, 320. If I subtract the numbers that I already have in the circle, 120, 160, and 30, that would give me the amount that only like rap, which is just 10. And you could do the same thing for rock. 395, subtract everything that is on the circle already. I don't know. I think I wrote. Well, I did write some of those things. They're right here. But so if you do 395, it is here. You can add all of these numbers, 120, 160, and 85, and subtract them from 395. And that gives you 30, and that's how you find that 30. Similarly, use the 295, add the sum of the numbers that are already inside the circle, and that tells you how many only like heavy metal. And last, if you add all of the numbers that are in all of the circles, this tells you how many out of the total. It was 495 students. If you subtract the sum of all of these numbers, then you get those students who didn't like anything, which they are not counted in these values. And the answer is 40, so they go outside. And with this, now you can answer all of the questions, huh? How many students like exactly two of the three types of music? We'll add 10 plus 30. I'm sorry, 120 in yellow. 120 plus 30 plus 85, which is 235. How many only like rock music? Well, the ones that only like rock, that was only the 30. That 30 represents only the ones that like rock. And last, the amount of students, how many students like only one of the three types of music? Well, now I would need to add the purple ones, which is 10, 30, and 20, because these are the areas that will represent only rock, only rap, only heavy metal, and the sum is 60. So by doing a Venn diagram, we were able to organize all of this information and find the answer. Okay, a little bit of logic. So some of the symbols that we study in logic was the not P symbol, which is called negation. We also did the what we call the conjunction, which is has to be both of them. We also have the disjunction, which is or, so it's kind of like a V symbol. We also have the if then, we call it the conditional, and we represent it with an arrow. And we have the biconditional, which is an arrow on both directions. Questions for this, they were related to writing in symbols, using those symbols, writing statements. For example, I have P represents today is Friday, Q represents, let me go back. It is raining, R represents I'm going to a movie, S I'm not going to the basketball game. So to write down this statement, today is Friday and it is raining, we can see that that's exactly P and also Q. And since we have the and, we would put the symbol that represents the and, which is kind of like a triangle. And you do the same thing for every statement. So on the next one, we have it is not raining. Well, it is raining is represented with the letter Q. The opposite would be it would have that symbol. I call it the wiggle, the wiggle symbol. So not Q. We have the and, so put the symbol for the and again. On the right, we have I'm going to a movie, so that's R exactly. So this whole statement is represented in symbols as wiggle, Q, symbol. You could say A or triangle R. For the next one, I have I am going to the basketball game. Notice that S actually reads I am not going to the basketball game. So if I say that I am, I'm saying the opposite. So I need to put wiggle line and then S, or the symbol for the or looks like a V. And I'm going to a movie. This would be R. So in symbols, this is not S or R. And then D, statement D says, if it is raining, then I'm not going to the basketball game. What you should be looking is for these words. If you notice, those are kind of like keywords. I noticed that it starts with if, and then it has the then in the middle. So it's an if and then statement. It's a conditional statement. So I'm going to need to have an arrow in there to represent it. And the answer is it. So the if and then is represented with that arrow. And then Q, it is raining because that's what Q represents. And then on the right of the then, after the preposition then, I have I'm not going to the basketball game. So this is exactly S. So in symbols, this would be Q arrow S. So a typical example in this section was actually the truth tables. And I would assume when I covered this section, I mentioned like make sure you ask your professor, will you have access to the truth tables or do you need to memorize them? And usually what we do is using these tables, we construct new ones. For example, here I have the symbols negation P and Q. I want to create its truth table. Well, the way that I like to do it is I start with the negation. It's like PEMDAS. Start with the negation. The negation is the opposite of P. So if P is true, the negation would be false. If P is true, the negation, if the P is false, the negation would be true. So it has the opposite letters. And then next, I put the values of Q. Notice that Q doesn't have negation. So exactly the same letters I put right under. And last, in between, I put the combination of those letters, the one on the left and the one on the right, according to the and symbol. So the and symbol has, and my table is a little bit small. here. So if you have true and true, the and would be true. If you have true and false, the and would be false. In fact, the and preposition or conjunction is only true when both of them are true. So if you go back to the table, notice that if you have F and T, then that would be false. F and F, that is false. You have two truths, so that's the only time when you get a T. And you have true and false. Since there's a false, then it makes the whole statement false. Okay, so that actually, this is my answer. The answer is the one that is in red. So notice that I wrote like 3 different things on this truth table, but that's kind of like my final answer. This is another example. I have longer symbols. This actually works using PEMDAS. So when you're doing your table, you would start with the negation, which is kind of like the first thing inside the parentheses, the first thing that you do. And then you go and do the Q column. And then you do the OR using the OR table, which I have right here. So you'll see that that's what I filled out. Now that I completed the parentheses, I work my way to the left. Like now I can go outside of the parentheses, which gives me the values of the green. Literally, since outside the parentheses, I have the negation, all that I'm doing is writing the opposite letters. So if it was true, then I get false. If it was false, then I get true. If it's true, I get false. And if it's true, I get false. And then I have a Q, so I do my Q. And finally, I combine the green with my last letters, my last column, to get these ones in blue. And technically, this is my final answer. These are the truth values for the entire symbol. Okay, so I noticed that I'm getting close to the end, so I'm going to stop here. If you want to, I do recommend that you download the entire PowerPoint. You should be able to download it. I'm going to post it just in case you want to download it.
Okay. Is that it, Mr. Tintos? Yes? Thank you.
Yes.
Thank you so much for presenting today, and thank you all for coming and being such a wonderful audience. And as we wrap up for the final review and last presentation for the TVE Happy Math Hour, we want to thank everyone and also remind you we have our Tejano virtual events every Friday at 1 p.m. So join us then and have an amazing weekend and good luck with your finals, everyone. Thank you. Bye.